All right, we're going to start our last problem uh, using the method of undetermined coefficients. Well, actually, here we're not even using that method, because it doesn't work with an impulse. So we have an impulsive input here. We have the same differential equation we've been using, the same initial conditions. We just have an impulse here now. All right. So what did we do last time? When we had an impulse, we integrated over the impulse, and we noted that if you integrate over a change in position, uh, you get zero. So that was the key result. Now, here we have a second order system, so we need to do this process twice. The first time we're going this in the when we do it the first time, rather than just go 0 minus to 0 plus, we're going to go to t, and we do that because that's going to allow us to have a second integration to get a second equation. Then we'll let all the t's go to 0 plus. So here I have all my equations, and I'm going to integrate them from 0 minus to t. I'm just letting t be a variable so I can get another equation. So if I do that, let's go down to the next thing. When you integrate the impulse, whether you integrate to 0 plus or t, it doesn't matter because of the sifting property. The impulse only goes to 0 plus. So we wind up popping out 9 anyway over here. So that's kind of boring. All right. So on this side, we're going to integrate this 0 minus to 0 plus. So we integrate the double derivative. We get y dot minus y dot is 0 minus. But here we have this as a t here. But y dot is 0 minus, well, we know that. That's 4. There, that is. And then we integrate the velocity. We get y minus y is 0 minus. Well, that's 2. Okay. And I should probably put in a y of t here. There we go. And so now we can bring these constants to the other side. We have 9 here. Let's see, that's minus 6 and minus 2. So that looks like that's going to become a 15. But that's times 6, so that's 12. So nope, that becomes 25. All right. So now I look at what do I have left in time? I have y dot plus 6y equals 25. So now I'm going to do this integration gig again. But this time I'm only going to go to 0 plus. So I'll take these things to 0 plus. So, and before, if I look at this thing, I took this to t, all right? But even so, this is just integrating over y. Whether I go to 0 plus or anything, once the impulse is over, it's all done, right? So I'll let the t go to 0 here and wipe that term out. Or let me restate that. So here this went to t. And now I'm going to integrate this to 0 plus. That forces this t to end at 0 plus. So that term wipes out. And now I'm integrating these two, which becomes y is 0 plus minus y is 0 minus, which we know. And then this becomes another integration of y. So that term goes away. And then this is a constant, 25, 0 minus to 0 plus. If we integrate a constant over no time, we get nothing. So now we have y is 0 plus minus y is 0 minus, which is a 2. This is a 0, this is a 0. So that says y is 0 plus equals 2 if we solve this one. All right. So let's see where we are. We have the first equation gave us y dot of 0 plus 6y of 0 plus equals 25. And we can substitute in for y of 0 plus equal to 2. So we have 6, 2, 12. Bring that over. We're left with y of 0 plus equals 13. Now, this can be a little confusing. Notice we had to get two equations here. So here was our first equation, all right? So we had this equation, all right? And then we did this made the second equation, that told us what y0 plus was. It's 2. All right. So we can stick this equation here, just to be clear, it came from right here. So we have 6y0 plus. We know what that is. Okay, we stick that in. And then we have, this is y dot of 0 plus. So we're just solving for it. That's how we got that 13. All right. So what do we know now? Y of 0 plus is 2. Y0 minus was 2. Y0 plus is 2. So the position hasn't changed, but the velocity has gone from 4 to 13. All right. So now, once we've done that, what all this says is this is the instantaneous change, and so now we just have an initial condition response. So we have the same differential equation, y double dot plus 6y dot plus 18y now equals 0, where the initial conditions are 2 and 13. And we just solve those in the usual way. So here's our complementary solution. Since we have complex roots, I'll just stay with the cosine. A e to the minus 3t cos 3t plus phi. This is simply determined by, once we know the roots, we can pick our form. So I now set y of 0 equal to 2, and familiar solution, 2 equals a cosine theta. All right, we take the derivative, which I do here. That has to equal 13. All right, substitute in a cosine theta equals 2. Okay, that would be minus 3 times 2 is minus 6. Bring this minus 6 to the other side, we get 19. Divide by the 3, and we are left with a sine theta equals 19 over 3. And I'll note this is actually wrong here. This should be minus 19 over 3. All right, so we put that in. And so we get a. A cosine is 2. Here's a sine minus 19 over 3. So we have this squared plus this squared, square root gives us 6.64. All right. So we'll notice that the a cosine goes in the positive x direction, and this is going in the minus y direction. So that gives us a phase of minus 72.5 times pi over 180. So again, you would take a sine theta over a cosine theta would be the tangent of theta, or in this case, phi. All right. So we substituted those in, and we're left with the solution for what the thing does after the impulse, 6.64. Darken them up a bit. E to the minus 3t cos 3t minus 72.5 degrees pi and 180. And it's time to move on. I'll talk with you again soon.